Okay, you're recording.
Okay, so we are here at the FE exam tutoring. I don't know. I don't know. Anyway, so finally we're gonna get the beginning of this thing, which I think is the first time we've ever done that. But right, Dylan? Got the beginning? Yes. Last time we missed the beginning, and the time before that the video was just awful. So we're gonna start with problem 33, which is the beginning of the signal processing section, which really just means signals and systems. So the first problem starts with an analog filter shown by the block diagram given here with this in drawings. There you go. Shown there, and so this filter shows an output that's sampled at a frequency at 10 hertz to provide the sequence y and t over here. If x of t equals 0 for t is less than 0 and x of t is 1 for t is greater than 0, which is a step function, if you remember right. So x of t equals 0, that's not right. X of t evaluated at t equals 0, and x of t greater than, where t is greater than 0 equals 1 is a step function. You guys remember it looks like this? It's all well and good. So we know it's a step function, which is important later. The next, actually, I'll put that there. Just need more space. So based on that, we're trying to find y of t, which we know this is in the frequency domain. So we convert this into the frequency domain. Do you guys remember how to do that? Laplace transform of a step function is 1 over s. Remember that?
Mm-hmm.
Yeah, vaguely. So you take this and you multiply it by the function inside, which gives you 5 times s plus 5, right? And I need more space. S. All right. So we have s and times that. Then what we do is we take that equals y of s, right? So now we need to take this and take it back into the time domain, which we do with an inverse Laplace. But to do an inverse Laplace, first we need to do what? You guys remember? We do partial fraction expansion so that we can find the values of this from the tables, because this by itself doesn't have an easy, fun value. So we do partial fraction expansion, which is 1 over s times 5 over s plus 5 equals a over s plus b
over s plus 5.
This is looking familiar, right?
Mm-hmm.
So then what we do is, or what I did, lots of people do this, there's like at least 3 different ways to do this. The way that I always found is you just cross multiply, so you have a times s plus 5 plus b times s equals 5 times 1, which is 5, right? You guys know how to do this, right?
Mm-hmm.
This particular system. So then you have as plus 5a plus bs equals 5 plus 0s, which makes it easy to do math. 5a equals 5, and then as plus bs equals 0. A equals 1, you divide by 5 on both sides. Then you plug it into here and you get b equals negative a. The s's cancel. So you get b equals negative 1. So then you have 1 over s plus negative 1 over s plus 5. Right? So then once you have that, then you go to your formula, which I don't have with me, and I'm really confident are on the booklet. But you plug it in the formula, and you get that. And the notation looks like this. Looks wonderful. And the formula that you get is that this one comes out. What is this?
U.
Exactly.
Yeah, step function.
It's constant, which is 1. and then u of t, yes, which will move to the end. So it's 1, and then the next one is minus, and this one is e to the negative 5t. What'd you say?
I was too tall.
Were you really?
He blocked the camera.
Okay, well, anyway, I'll rewrite it over here.
You're good. Well, you're good now.
Y equal, yeah, but now I'm really good.
Okay.
Y equals 1 minus e to the negative 5t, like that. So that is our y of t, and it should say y of t, not just y, but whatever. So, we're not done yet. The next thing we're looking at is we want to know about the sampling at 10 hertz. We want to know what, we're looking for just the series of values. So we're just going to we're sampling it, so we want to know every value. So what we're going to do is we're going to start at 0 and start at 0. So we have this y equals nt. So t is 1 over 10 hertz, right? Which is 1 over 10, which equals 0.1. So we're sampling it at 0.1 n. So all we're going to do is plug this into this, and then read out the values. So the first one is 1 minus e to the negative 5 times 0.1, which equals negative 0.5. So we have 1 minus e to the minus 0.5, right? And then we do calculations and then keep going and get our numbers. I'm not going to do actual math. I'm just going to leave it there. Hmm?
We don't do actual math.
We don't do actual math here. We consult a formula, or we do some crazy algebra to consult a formula to then plug in some numbers. And that is how you find the answer to that one, which is essentially not important. Well, yeah, it is important, but I'm not going to do it. Because we all know how to plug in numbers, right? I hope. That's algebra 1 back in high school.
Otherwise, this exam is going to be really difficult. For you.
Otherwise, this exam is going to be really, really tough. All right, so moving on to 34. 34, we have this very fine formula, and we want to know what kind of filter it is. Are any of these filters easily, do you guys know what these first two are? That's a good
Nope.
question. Anybody?
No.
All right. We actually asked Dr. Nee about this one, and she said she barely talked about it. So.
So can
That's
we
fine.
assume this will not be on the test?
They probably not, but who knows? The test doesn't even know. So anyway, the first one, this one's called a finite impulse response, and this one's called an infinite impulse response. But we can come back to that part later. First off, what do we know about these ones?
Let's say killer or filter.
Filter. I can't write.
Also, yes.
First order.
First order
Killer.
digital
Yes.
killer.
All right. One of the things that's pretty obvious is you know it's not first order because
There's a squared.
it's not first order. Very simple. So we know it is not C, right? Also, second of all, what does causal mean? English. What is cause?
It is affected by previous or subsequent values.
It isn't. It's not caused. It's not caused by anything. So it's not impacted by the input. This one obviously impacted by the input, right? So we know that this is not true. It is caused by the input, so it's not non-causal. So now we're just left with what these are. And as I said before, it's finite impulse and infinite impulse. So what we do is we need to know what happens when you plug in an impulse function. So what we're going to do is make x of n equal to an impulse function, which, as you guys remember, is shown by the graph where it's 0, 0, whoa. At every negative value, it's 0. At 0, it's 1. And at every positive value, it's 0. You guys remember that? I really can't write. Right? We talked about that like last week, so you really should do. Yes. Anyway, So we're going to plug in the impulse function, which is also represented by the sig. Actually, I can't draw sigmas, wouldn't I? Or deltas, or whatever it is. I can't draw them, so I'm not going to. It's represented by that. So what we're going to do is, what did I do? Oh yeah, okay. So we have x of z equal times, go back to our definition from over here, x of z times 1 over 1 minus 0.2, z negative 1 minus 0.1 z negative 2 equals y of n, right? Definition from earlier. Multiply this on both sides, so we get x of z equals y of n. Oh. Now we're in discrete stuff. Well, no, we are. Wait. This should be x of n. That's what's confusing me. X of n times this equals x of n. One minus 0.2 z negative 1 minus 0.1 z negative 2 y of n. Okay, so that's all multiplied. Wonderful. And then the next step we do is we take then you start to plug in values. That's what you do. So we know that what's it called? We know that as we plug in things. Oh yeah, so then you do the inverse Z transform of this, which is basically converting this Z minus 1 equals N minus 1, and Z minus 2 equals N minus 2. Is that looking familiar, maybe? No. Oh, okay, so we take this and we plug this into all the Z's, and then you start out with, and then you just plug in an impulse function to this. So we know that x of 1 is, or x of 0 is 1, and everything else is 0. So when we do this recursively, the first one is, it's actually probably better to leave it up here like this. But anyway, you plug in to, oh no, it's not. Okay, anyway, so this goes over to x of n equals y of n minus 0.2 y of n minus 1. Okay, so we end up with that. Then they do some fancy cool stuff to, I think it's called they call it the switching principle, the shift problem. They come up with this. This is a y. Whoa, I can't draw. Y of n equals x of n plus 0.2. Wow, really? Okay. 0.2 y of n minus 1 plus 0.2 y of n minus 2. Okay, so you can see what they did there. So we start off with it is 0.1. Yeah. Forgive my algebra. Okay, so then we start plugging values. We know that before the impulse function, everything's 0. So this is starts at 0, so this is 1. No, sorry. This is what we're looking for. So the first one we're going to go is y of n equals 1 plus 0 plus 0, which gives us 1.
Should be y of 0.
What?
Should be y of 0.
Yeah, it should be y of 0. Okay, so then y of 1 equals 0 plus 0.2. Oh, I'm sorry. So we know that this is a finite impulse response, right? And this is infinite. So to distinguish the two, we want to know if the y of n is finite or infinite, right? We want to know if it goes on forever or if it just ends at some point. It's like you remember when we were doing transient response. We want to know if the transient response will stop messing with our stuff. Yeah, it's the same thing. That's what we're doing here. We're just finding out if the transient response ever ends, right? Making sense?
So obviously the impulse if the y then ever hits 0.
If it terminates, we're done. Yeah. Okay. Spoiler alert. It won't. I'm only going to do a couple of terms, but it's just going to keep going on and on and on. So this is going to be plus 0.2 plus we're back at 0, I believe. Yeah, we're back at 0. So then you go to y of 2 equals, and then this is going to be 0 plus 0 plus 0.1. No. 0. What? Okay, so let me catch my breath again. Okay, this is 0. 1 above was 0.2. I think. If I can do my math right. Hold on. This one's 0.2. So then we plug in, this is going to be 0. Then y of minus 1 is 0.2. Yeah, so I was right. 0.2 times 0.2 plus, and then 0.1 times 1, right? Yeah. Okay, cool. That's messy, but whatever. So then you come up with, this is 0.14, and then we're just going to keep repeating with numbers, and it's never going to end. Do you guys see that? It's going to keep going on forever. It's just going to get smaller and smaller, but it'll never actually reach 0. So anyway, plugging in numbers, we don't do real math, so we're just going to stop there with our real math. And if you don't believe that it goes on forever, what? The answer is, it goes on forever, so therefore the answer is it's infinite.
Infinite.
So that's that problem. Yeah. Okay. So moving on to the next one, because we got plenty of problems to do. Not enough time to do them. We're moving on to 35. Are there, oh, before I do that, are there any questions about this one? Cool, awesome. 35. We have if x of n equals 120 sine of 3/2 pi n, what is the what is the function at y of 2? So at y of 2, we want to know what the output is at time 2, at sample number 2. So easy way to do this is to kind of just go through it. Some important things to know is what happens at this z of -1. Like, anyway, the way what happens over here is important. So when you put x of n through a z of -1 block, it comes out being x of x of n minus 1. And that'll happen, we saw that kind of over here with this one. When you do the transform, it turns into n minus 1. So going over here, this can translate to x of n minus 2, and this can translate over here to x of n minus 3, and this can translate to x sub n minus 4. Everybody see where I got all those? Making sense? Okay, so, and then these are all going forward. So, that may not have been obvious before, but everything is going forward. There's no actual feedback. It's just a feed forward circuit. Yeah. So we have this. So what we do is we take x of n, we multiply it by 1, and we add it to x of n minus 1 times 1/2. And then we take it at x of n minus 2 and multiply it by 1/4, and add those together. And then take x of n minus 3, multiply it by 1/8, then add those together. X of n minus 4 multiplied by 1/16, and then add those together. So it all comes out to one nice sum of all the previous things. So you could, if you wanted to, rewrite it to be x of n times 1x of n plus 0.5. Well, I wrote it as 1/2 for a reason. 1/2 of x of n minus 1 plus 1/4 x of n minus 2, and I'm so going to run out of room, plus 1/8 x of n minus 3 plus 1/16 x of n minus 4. Okay, so all we have to do is evaluate it at each of these points and then add them together, right? So we take this, x of n is equal to 120 sine 3 pi n over 2. So we take 1 times, so it'd be 120 sine of, oh, we're doing it at 2, right? So sine of 2 plus 1/2, 120 sine, whoa, I can't, it's wrong, nobody corrected me.
I was going to say, isn't it 3 pi
3 pi over 2
times 2? So it's just 3 pi.
Yeah, it's just 3 pi. So I'm going to make it neater. Okay, and then this is 3 pi over 2 times 1, thank you, plus, and then the other one's 1/4, 120 sine 3 pi over 2, and then this is 0, right?
Mm-hmm.
And then this is plus 1/4, 120 sine, no, it's not 1/4.
1/8.
Sine of 3 pi over 2 at -1,
Mm-hmm.
and then plus 1/16, 120 sine 3 pi over 2 times -2.
2.
Okay. So then we take that and we evaluate it, and we get, this is 0, because it's 3 pi, which is, I can draw a circle for you. Alright, so 3 pi takes you to right here, which sine is 0. And then you can add 1/2, or not, well, I'm just going to do math again. Plus this one, which comes out to be, wait a second. Oh no, that's why. Okay, this is 1/2 times 120, because sine of 3 pi over 2 brings you to right here, which is 1. And then you have plus 1/4 of 0, because we're back to 3 pi again. Actually, we're at 0, which is right here, which is 0. Plus 1/8 of -1, which gets you to -120, because it brings you to right here, which is, again, self-explanatory, plus 1/16 times 0, for the same reasons as before. Confusions, sine, cosine, brings us right This one's 3 pi, which brings us back over there to 3 pi again. Actually brings us to negative 3 pi, which brings us to the same place. So when we add these together, we have 1/2 of 120 equals 60, and 1/8 times negative 120, which equals 15. Can't do math. Right?
Yes.
Yeah, so then we add those together, we get 45, which should be the right answer, in theory. I did it wrong somehow.
Dang it, Jordan.
I know. What's up with that? Oh, that's why. Because I'm dumb. This one is negative, and this one should be positive. Right? Based on my signs. Maybe not.
Why?
Let's see. Sine of 3 pi over 2 should bring you right here, which is negative. That's why. Yeah. And then when you go the other direction, it brings you to this one, which makes it positive. So yes, my sign is wrong because I went the wrong, I didn't do actual math. Shame on me. So
You're
you
a
get
bad engineer.
negative because this is positive and this is negative. So you get negative 45. Anybody unclear on all that? On the math? If you guys remember, I'm terrible at algebra. I've been doing algebra badly every single time, so who hired you? That's the problem, right? He hired me back in the back.
I didn't want to do it, so I delegated it to Jordan.
Yep.
My bad.
And I might have volunteered too. Okay, so now we're on to 36, which is the next one. And when we go to 36, the problem is, what is the minimum sampling frequency for this equation here? Did I write it poorly so you can't read it? Maybe? I don't know.
Cosine of
100
100 pi t plus sine 200 pi t plus sine 60 pi t.
Yep, so we're looking for the minimum sampling frequency. Anybody remember how to do that? No. Resounding no. All you have to do is you take the largest frequency and you multiply it by 2, and there you go. Minimum sampling frequency.
So 400.
So you would think that. It'd be 400 pi, right? Anybody else thinks 400 pi? It is 400 pi, except that this is
Radians per second.
radians per second. Which means we have to be very cool and convert this to hertz. Maybe don't hurt me. No more. No more. So we convert this to hertz. So we take 400 pi and divide by 2 pi, and we get
200.
200 hertz. So Dylan, you're absolutely right. Just I didn't tell you that the answers are in hertz. Shame on me, right?
That's all good.
Yep. So here we go. 200 hertz. Nice and easy problem. Now we move on to 37, unless you have a question about that one. No. Okay. Good. Pretty easy. Now we're on 37. We have a sampling frequency of 30 hertz, and we have this very nice signal that we want to sample at 30 hertz. So what we want to know what the resulting x of n equals at that sampling, which sounds really complicated, except that all you have to do is the same thing that we did over here in the first problem. You just take this n of t and you plug it in for t. Really simple. So first we need to find t, which is 1 over t equals 1 over f, right? That's how that works. Which equals 1 over 30, which I'm not even going to bother simplifying because it's easy to plug in. I am going to write it better though. 1 over 30, there we go. Okay, so we have 1 over 30. Now we're going to plug that in. Oh, and n. because here I'm going to talk for a bit. When you have a sampling frequency, you basically want to just see what you're going to get at every time you take every time you sample it. So what you're going to do is you're going to take the first value and sample it, take the second value and sample it, and those first, second, thirds are represented by n, and then multiplied by the time in between each sample. Pretty straightforward, but just in case you're confused on how this all came about and why we're doing it this way and just plugging this right in, that's how that works. So we are on 37. So what you do is you end up with 5 sine of 20 pi divided by 30n plus 4 sine 30 pi over 30 and then n plus 3 sine 40 pi n and 30. So you come up with all these, and that's Rx of n. And then all you have to do is simplify. So this becomes 5 sine 2/3 pi n plus 4 sine pi n plus 3 sine 4/3 pi n. Awesome. And then when you do this, you realize, you say, but wait, what's sine of pi? Go back to our triangle, our circle over here. I'm not going to redraw it, unfortunately.
0.
And it is 0. So we know that every time if we multiply it by 1, we're going to get another 0 and another 0 and another 0. So all we have to do is get rid of that term. And now we only have 2 terms in our sampled answer. So it comes out to be x of n equals 5 sine 2/3 pi n plus 3 sine 4/3 pi n. Yep. Did I do anything wrong on that one? Mathematically, algebraically? I think not. But anyway, any questions on this one? Awesome. Now I can move to the other side of the board again. Woo! All right, now we're on 38. 38, I think, right? Yeah.
Mm-hmm.
38, we're given a block diagram that looks like this. X of n, the box, to y of n. And inside the box we have 1 over 1 plus minus, no, plus 3z negative 1 plus 2z negative 2. That's a 2, I promise. Okay, so we have this, and we want to know what the, we want to know if the filter is stable. Wow, I can't write. Okay, we want to know if it's stable, question mark. So, does anybody remember what tells if a function, if a filter is stable or not? John, do you remember? Nope. Okay,
Poles
well,
are on the left-hand side.
Poles are on the left-hand side. That's absolutely right.
Oh,
For analog signals, for x of t or x of s, whatever, for Laplace transforms, they are, if the poles are on this side of the equation, it is stable. unfortunately, we are dealing with Z transforms,
Hmm.
which are stable inside this circle. I think it's
Stupid
inside the
circle.
Yes, inside the circle. Yep, and this is a unit circle, as evidenced by the fact that it's equally centered, and every intersection is the distance 1 away from the origin,
Perfect.
right? That's a perfect circle, right? So, we want to know if they're in here, they are stable, and if they're on the surface, they're marginally stable. And if they're outside, they are unstable. And of course, this is the I, and this is
R,
something.
real? Would it not be real and imaginary?
It's not real, it's, I guess it is real. I don't think they use R, but we'll use R, because we can.
For all intents purposes.
They use RE, capital R. Yeah, capital R. They use RE. I kind of like the lowercase r better.
Meh.
Whatever. We'll be right this time. And they're weird. They use IM like that.
Still imaginary and real.
It's still imaginary and real, but they do it like that. I don't know. Anyway, so all we have to do is find the poles of this transfer function, which are really difficult to find, right? You just take 1 plus 3 z minus 1 plus 2 z minus 2, and you can take the characteristic equation, which is easier to work with, but I'm just going to pretend it's the characteristic equation, which you guys remember just replaces these with s, I think, or something. I don't know. Anyway, so what you come up with is you come up with the pole, you set this equal to 0, and you come up with the poles equal 1 and 2, except they're negative, because you have to subtract to get the poles. So, you guys don't remember algebra, so you guys need to know how to do that. So I don't need to tell you. That's not how you represent it, though. You use these cool brackets, because
Why not?
it's a data set, not a point. So, and then the imaginary portion of these poles is obviously 0, but we're not going to talk about that. So we look at this and we notice that this one is on the circle, so we know that it's marginally stable. This one is, but this one is outside over here, which makes the whole thing unstable. So we know that it's not stable. And it's a big deal because unstable filters are sad. They're not useful most of the time, I think. Anyway, we don't need to worry about that. That's just the answer. So now we're on to 39, which is our next problem, unless somebody has a question about 38. I didn't think so. You guys are a very unquestioning bunch. I must be just that good. I'm that good, I know.
We begin to remember as you go.
Yeah, I hope so. That's how I work. All right, so we're skipping 39 because 39 is not fun. We're just skipping it.
That's fine.
Yeah,
Not
we'll talk
fun.
about it. Dr. Nee can talk about it probably when she talks about stuff whenever we're having our review for that thing.
For what?
Yeah, so for Dylan, we went to Dr. Nee's office to talk about this stuff, and she said, if you want, I can offer a tutoring session for you guys for controls and signals, and we said yes. And she said, just tell her what day and time that fits in her schedule, which will probably be either Wednesday morning or afternoon or Friday afternoon, depending on what we're sending out an email to ask people what to think about that.
All right, sounds good.
Yeah,
So everybody listening, make sure you pay attention.
check your email, vote, and then come, because Dr. Nee's way better at this than I am. Yeah, so now we're on problem 40, which is infinitely easier than 39. And problem 40 is electronics. So for this question, a voltmeter is used to measure the voltage across a resistor. So here we have a resistor, and you use a voltmeter to find the voltage across it. So, you're using a voltmeter to measure the voltage across the resistor. The voltmeter is connected parallel with the resistor, which is what you do when you calculate voltage. To obtain an accurate voltage reading, the internal resistance of the voltmeter must be what? So let's say this is 100 ohms. I don't know. What do we know conceptually about this resistance over here? We know that it's the same size, that it's really big, that it's medium.
Don't remember.
So the question is, to obtain an accurate voltage reading, the internal resistance of the voltage meter must be, and then your choices are much smaller than the resistance whose voltage is being measured, equal to the resistance whose voltage is being measured, equal to twice the resistance whose voltage is being measured, or much greater than the voltage much greater than the resistance whose voltage is being measured. Those are your four options. It's got to be as big as you can get it. We want this resistance to be as close to infinity as possible, right? Because then we get an accurate reading. It won't be infinity, but in our problems we always treat it like that, right? So that it doesn't take up currents, so that it doesn't mess with our system. When you get into high voltage systems, I think you have to worry about that, right? Drawing current, pulling out the fuse and whatever. I don't know. Anyway, that's all fun. Actually, I should draw that again, just for fun. I should have erased it. All right. There we go. Now I have better notation too. Okay. Now we are in 41. And a meter movement has an internal resistance Rm of 5 kiloohms. And full-scale current of 50 microamps. I shouldn't put it there though. Okay, then the meter is to be used in a design with a voltmeter with a full-scale voltage VFS. So this is IFS and VFS equals 20 volts. So I want to know what is the value of the resistance R series that creates this scenario. So we want the voltage and the current to be, we want the voltage across both resistors to be 20 volts and the current through the whole system to be 50 microamps. So to do this problem, we go through V equals IR. V equals 20 volts equals 50 microamps times R, where R equals RS plus 5 kiloohms. So then we plug this in here. We'll do the Dr. D method. So then we have 20 over 50 microamps times this. No, equals this. And then we have this. Then we move the 5 kiloohms to the other side, so we have 20 over 50 micro minus 5K, I believe, if I'm not doing anything wrong. And yeah, I'm doing it right. So then we get, this is 400,000 is what this comes out to. So 400,000 minus 5,000 gives you 395,000, which I can actually simplify to K There we go.
So what was the question of this again?
The question was, what's R series?
To accomplish the current or?
To accomplish this scenario, to make the voltage and current relationship true.
Oh.
Yeah. Because I mean, regardless of what this R series is, maybe it's a current meter, so or a current source. So the current through this, no matter what the resistance is going to be 50 micro. So we want to make the voltage true. Conversely, this could be a voltage source of 20 volts, and we want to know the current. But which one it is not really given. We're just assuming one or the other. We don't really need to know.
Actually, both. It's a current and a voltage.
Yeah.
On top.
Yeah, it's actually both. So now we're on problem 41. A meter movement has an internal resistance Rm. No, I did that one. That's 41. Guys, why don't you stop me? All right, so we're on 42. All right, so we're on 42. 42. That's 41. A sine wave generator is connected to the vertical input of an oscilloscope. The oscilloscope has a horizontal screen of 10 centimeters and a height of 8 centimeters. And if the sweep speed of the oscilloscope is set to 4 ms per second per centimeter, 4 ms per centimeter, and the number of cycles on the screen is 4, so it looks like this. Wow, I can't draw. Let's try that again. So it looks something like, wow, oh, that's
Should have drawn the wave first and then drew the box.
No, it's perfect. All right, so there's four cycles in there. We're kind of pushing the limit, but it's perfectly 4. So we're looking for the frequency of the sine wave that we're looking at. So with four periods in there, we want to know what the frequency is of it. So to do this, we take the number of cycles per the length, which is 4 cycles per 10 centimeters. Then we go from centimeters to milliseconds, just this. And then we go from that to milliseconds to seconds. And then we're getting cycles per second, right? Which is frequency. Yeah. So we have 4, this is going to be 1, this is going to be 4 up here? No. 1 over 4. Yeah, I can't read. All right, and then this is going to be 1,000. Cool. Okay, so we do all the math. We don't do math in here. And you get 100 hertz. And if you don't believe me, 4 cancels with 4. 10 cancels with 1,000, kind of give you 100.
Kind of.
Concerned about those extra zeros.
Kind of. It loosely cancels. All right. But you end up with the right answer. Like that. So now we are on 43. All right. 43. The intrinsic carrier concentration of silicon under room temperature is,
Swapping section.
we're still in the electronics section. We're just in the 3rd chapter of the electronics section. So Ni
Elvis.
equals 1.18 times 10 to the 17? Is that right? No, 10. Centimeters negative cubed. So with that, we then know the next thing that it says is that a silicon crystal has a hole concentration of P equals 3 times 10 is 10 squared centimeters negative cubed. Okay, so we're looking for the electron concentration. We're looking for N equals. All right, and you guys remember the formula for this is NP equals Ni squared, which comes out to N times 3 times 10 squared equals 1.18 times 10 to the 10. Divide by both sides, you get N equals 143. 4.6 times 10 to this times 10 to the this is squared, remember? Times 10 to the 17 centimeters negative cubed. Very simple problem, very simple math. Moving on to 44. In metallic materials, this was conceptual. In metallic materials, electric current occurs due to the movement of electrons. In a semiconductor, there is one type of current flow. There are 2 types of current flow. 3 types of current flow. And 4 types of current flow. One of them is right, one of them isn't. 3 of them aren't, actually. So,
One is right, the rest I don't know.
going
Maybe.
through this, we know that there are electrons flowing one direction, right? E minus going that way. And we also know that there are positive holes, I guess they're called, going the other direction, right? And then, is there anything else flowing in a semiconductor? Magic. Unfortunately, we don't deal with that. We pretend it doesn't exist. So we're gonna go with 2 for this one. One way to remember this is you have the physicists who like watching current go in one direction, and you have the engineers going another one. So you have 2 types of current. One for physicists, one for engineers.
Perfect.
And that's 44. Now we're on to 45, which is a problem that we do occasionally.
Pretty sure it's not negative 45.
Yeah. Because then I have to go backwards through the other problems. Alright, so 45. We definitely did not do this. Yeah, so we said no to that one. So we're going to do 46. If you want to know what 45 is, a silicon crystal is 5 millimeters long and has a rectangular cross-section of 20 micrometers times 40 micrometers. The donor concentration, Nd, at room temperature is 5 times 10 to the 15 centimeters negative cubed. A current of 2 microamps exists in the crystal. If the mobility mu n of an electron is 1.5 times 10 to the cube centimeters squared over volts per second, and the charge of a hole is Q equals 1.6 times 10 to the negative 19 coulombs, the voltage V across the crystal is most nearly, lots of fun stuff.
Question mark.
Question mark, yes. And I think you guys can remember we did that problem way back when. I didn't feel like dredging up my memories like that, so I didn't do the problem. So we are going to problem 46. For t is greater than 0, the output of an operational amplifier is, so for t is greater than 0, the output of an amplifier is V naught, I did 46. Okay, V naught T equals 10 minus 10 e to the negative T over 200 times 10 to the minus 9 seconds. So we have this formula. The output is connected to a logic gate that requires, so this is connected to a logic gate, which could be like an AND or an OR. Anyway, so we can make it an OR. And so this needs a,
It's just one leg.
is that not what an OR looks like?
There's a second one. There's a second leg.
Yeah, but we don't cover the second leg.
Grounded.
Great. Alright, to register a 1, it requires 4.8 volts. So we want to know what is the approximate time required for the amplifier to reach 4.8 volts. We want to know the delay in our circuit. Given. All we have to do is find out when this equals 4.8, right? And then find t. So, really simple. 4.8 equals 10 minus 10 e to the negative t over 200 times 10 to the negative 9 seconds. So we take this, we subtract 10, we subtract 10, we get 5.2 negative equals negative 10 e to the negative t over 200 times 10 to the negative 9 seconds. So then we divide by negative 10, divide by negative 10, we get 0.52 positive equals all this stuff. That is really fast. We should have learned that like 3 years ago.
That's the doctor.
This is the Dr. B method.
I get it.
You're not in,
No.
okay, today he did this and he said, on tests, if you're trying to go through things really fast, you do this. And so I'm trying it out.
Yeah.
Fun. So anyway, you do this, then what you do is you take the ln of both sides, ln, and then, yeah, ln. This comes out to be some number. I didn't record what it was, because who does math? And it comes out to be negative 0.654 equals ln of this thing, which is just negative t over 200 times 10 to the negative 9 seconds. So then you multiply by this, you put this on the other side, and you get the answer, which is 1.308, sorry, 308 times 10 to the negative 7 seconds is your time, which for our problem is represented as 130 nanoseconds, which is 130 times 10 to the negative 9. Cool. It's 46. Now we're moving on to 47, I believe. Yes, 47, which I did on the computer. So we might not be going straight to 47. Nothing happened. Alright, and that'll power up, and while that's powering up, we'll do 48. We've got a time limit to do 13 more problems, so getting done.
Easy.
Easy. How many problems have we done so far? Started at 33. We're on 48, 47. We've done 13. We're almost halfway there.
But we skipped like 2.
But we, hey!
So we've done 11.
Yeah, okay, so we're moving right along. I think we're on time. 48. What is the rise time for the waveform shown? You probably want to see the waveform, which looks like this. Kind of. You know my drawing's always perfect. That's not a right angle. This is 48. This is a right angle box. This is 30 volts. This is 28 volts. And this is 5 milliseconds. Yeah. And this is 10 milliseconds. There's another right angle box for you. Okay, cool. And there we have all the information that we need. There's more given, but that's all that's important. So, what we want to know is the rise time.
It's just unextended.
We're gonna fix that.
God bless you.
Cool. Perfect. Alright. I'll finish this problem first, and then we'll move on to problem 47. 48. Okay, what did I say? Oh yeah, so what is the rise time for the waveform shown? We want to know, wait. Yeah, what is the rise time for the waveform shown? So we want to know the time it takes to get from here to here, except we want to know the time, we don't care, so we don't want to know the exact time that it gets to this point. We want to know the time that it gets to 90% of that. So, we know that it starts, at 5 and goes to 10, which is 5 milliseconds. And we could stop there and be like, yes. But the 10% point of 30 volts is 27 volts. And the 90% point is 3 volts. So what we do is we take those numbers and we subtract them. So it's 27 minus 3 equals 24. And then we do a ratio. We know that it gets to 30 volts in 5 milliseconds. So 30 over 5 equals 24 over T. T is a proper variable for this problem. So then you just 30t equals 24 times 5. T equals 4. 6 times 5 is 30. 6 times 4 is 24. So factor, do cool stuff. Or you can just plug it into a calculator like most people do. And you get that. And that is the answer to our problem. Any questions on that? Splendid. Let's move on to 47. We'll go backwards. So the question for 47 is, it should be drawn, actually. So we'll draw it over here. We have a JK flip-flop pictured over there. Subject to the input of the waveform shown, which look like this. We have J, which looks like this. I might need more space.
Very sporty.
Yep. 5, problem 40. You're so 7 problems ago. Or is it 6 or 5 problems ago?
Yes.
Yes. Alright, so this goes a little bit longer. Alright, so we're back to digital logic. You guys remember that, right? And then we have K, which goes like this. And then we have clock, which goes like this. All right, so we have these signals here. And we want to know what the output is. So basically we're going from we're going here, we're finding out the value is here, value is here, value is here, value is here. So we go back to what we remember from JK flip-flop circuits, like this one. So which says the JK flip-flop is, we can skip that part, and we go that the JK, if JK are both low, then nothing happens. If JK are both high, then the output will switch from whatever it was, from one state to the other. It also, that is very not helpful. Anyway, If they're both the same, then it'll switch. And if
They're different than it takes value.
yeah, I went too far. Okay, so yeah, and if they're different, then it takes J. So yeah. So if yeah, that makes sense to everybody. So with this one, J is 0, K is 0. What happens? Nothing.
Nothing.
The initial state, as given by the problem, is 1. So over here it's 1. So over here nothing happens, so it stays 1, right? Then we come to the next one, and they're different. So it takes the value of J,
J.
right?
So it's
So
0.
this is J, which is 0. Then we come over here. This one is 0, and this one is 1. So it takes, they're different,
J,
so it takes the value of J,
1.
which is 1, right? Then we have this one. They're different, so it takes the value of J, which is
0.
0, yes. And that is our answer. Our answer is 1, 0, 1, 0. Yeah, that's the answer.
The answer is A.
Our answer is A, yes. How'd you know that? What?
It's hexadecimal, 1010.
Which is also coincidentally A on our multiple choice. Somebody who was more clever than me. Alright. 48 we did. It's over here. 47 is right there. Now we're on 49. Logic gate output Thevenin equivalent. Did we do 49? No, we did not. We kind of did 49. So logic gate output Thevenin equivalent circuit is shown. It looks like this.
Are you going to use the computer again?
Oh yeah, I was going to do one other thing. It's not in the problem, but I thought it'd be cool to talk about it. Because we talked about JK flip-flops in digital logic, if you guys remember, a zillion years ago. And then we also talked about the SR flip-flop. Well, he called it a SR latch. The SR latch circuit shown here, like this. You guys remember this one? What it does is it takes it has this one which sets it to 1, and then this one which sets it back to the previous thing. So it also probably has a clock signal to tell it when to do things. Anyway, I just wanted to refresh your memory on the SR latch. If you guys remember it, we did that all fun tracing the iterative processes. Lots of fun. And yes, Dylan. Now.
Okay. Don't exit off of those. We can post those on the Facebook link.
Yeah, we can. We can also, yeah, there's one other. I'm using the computer one other time, but that other time, I did it mostly for me. And I can just talk about it. So, now we're on problem 49, which looks like that. And we want to know the gate drives wiring and cable capacitance, whose total value is 75 picofarads. We want to know how long it'll take to, what the delay is on this circuit. So when we put voltage to it, how long it'll take for the circuit to change. Anyway, I didn't want to talk about it except that it requires the time constant, which is RC. You guys remember from last time. So just remember that these kind of problems, they require RC, and to solve them, to find the time constant. And this one, yeah, I won't say any more about that one. We're skipping it. Problem 50. Problem 50 is, what is the 4-bit binary equivalent of the decimal number 13? (1101) is the proposed answer. Because you take 13 and you divide it by the highest highest power of 2. highest power of 2, which is 2 to the 3, which equals 8. So you subtract 8, which gives you 5. So then you take the highest power, which is 2 to the 2, which equals 4. And then you take that, now you have 1 left. So 5 minus 4 equals 1. So then you have 2 to the 0 equals 1. So then you subtract those and you get 0. And so you know it's 2 to the 0, which is 1. Skip to the 1, which is 0. Go to 2 to the 2, which is 1. 2 to the 3 is 1. Which is how Stephen did that, right? He just did all that crazy math.
Okay, that probably could be for me then.
Yeah, you could. You just have to do this.
That's right, yeah.
You'd have to write it down like this, like I did. So that's our answer, as proposed earlier. 51. For the digital circuit shown, what are the outputs at Y and Z? You guys got this one, right?
Yes.
Yeah. All right. So the circuit looks like this.
Wow.
That is not what it looks like. Alright, that's more like what it looks like. This is 0, 0. This is X. Which goes into Y. Alright. Since I suck at drawing, I figured I'd just write it.
It's actually ignoring man.
Picky. Alright. NOR and AND gate. So we take this one, or 0 with 0, we get?
0.
I am, yes. You're absolutely right. Singularly, just one. Alright. 0 and 0, we order them together, we still get 0, so x equals 0, but we don't care about x, we want y and z. So then we put it in here, and we get 0 and 0, we order them together, we get 0, which turns into 1,
Because
which
of the
gives us
NOR.
y is 1. Then we AND 1 with 1, and we get 0, and we get 1. And then we do NOR and NAND, and we make it 0, right? So z equals 0. So y equals 1, z equals 0. I should probably write down z equals. Problem complete. Now we're on problem 52. Now we've moved from, was that electronics? That was digital systems. Now we've moved from digital systems to computer systems, which sounds like it should be more complicated, but it won't be.
We're moving up in life.
We are. We're moving up in life. We're erasing 43. All right. Let's see. All right. Now we're on 43. No, we're not on 43. We're on 52. How many memory locations can be addressed by a 32-bit microprocessor? 32 bits. How many memory locations can be accessed by this? Anybody know off the top of their head?
4 billion.
4 billion. Which is, yeah. Yes, absolutely. And how did you get that? You went 2 to the 32, right?
Yes.
Equals 4 billion.
4 gigs.
4, yeah. I think it's a lowercase b in this case.
I guess it doesn't matter.
They wrote with capital B, but yeah.
I guess it's math.
It is because each address is a byte. So, yeah.
Gigabytes.
Yeah, so it should be, okay, cool. Plus it's a computer, I mean, we're high tech. Okay, so that's 52. Very nice and easy. This is 52. I should write down this 52. And this is 51. And now we go over here. And now we're on problem 53, right? How many inputs can a multiplexer having 2 selection lines have? That's probably right. I just don't have my notes over there.
2 to the 2.
Yes, 2 to the 2, which is definitely 4 because we did that earlier. Yep. 2 to the 2. If it was a multiplexer of like 8, we'd say, or wait, is that right?
What?
No. If we had, yeah, if we had a that is right. If we had a multiplexer of 8, it'd be 2 to the 8, right? Yes. Yeah. So very fun, very exciting. I didn't even need to write anything down. 53 equals 4. All right. 54. Consider the following circuit.
Okay.
Yes. What do you think about it?
It's quite clear, really.
Yes, it is. It speaks for itself, doesn't it?
Yes.
All right. So we have X.
Diode or an OR gate?
Hmm?
Is that diode or? Oh, wait, no.
That's
It's
a
not a diode.
That's the line.
that's a
Diodes
not.
look like this. Yeah.
I remember that.
Plus, we're in computer systems. We're not in electronics anymore. We don't do diodes.
Thank goodness.
Yeah. Hey, what happened to the diode problems? Where'd they go? We had 0 diode problems. All right. Z doesn't get an OR gate. So X because it comes in here. This comes this way. Then we have another one, and another one, and another one. Z goes to all of them. Then we have wait, that's not right. Leave it to me to screw up this problem. All right. So this is X naught, X prime, X prime, X, and X. And this is Y prime, Y prime, and this is also Y prime, I believe. Nope, I drew it wrong. This one's not Y prime. This one. Oh, screw it. I'm not going to draw it. This one's Y. And this one's Y. And then this one is, yeah, and then Z is all of them. There's no not Z's. Okay, so we know that this is, so despite my crude drawings, what we can do is we can take these and extrapolate them. So when X is, we know that this one is going to be, oh, this is F1, F0, F1, F2, F3. And what we want to know is, we want to know, is it a 2-bit compare? Is it a decoder? Is it a full adder? And then the last one is a full subtractor, which it definitely is.
Clearly.
Clearly. All right. Just for everybody on camera, why is it not a full adder or a full subtractor?
Full adders I know have exclusive ORs in there.
They have exclusive ORs in there. Yes.
It's two half adders which have exclusive ORs and gates. And it's not complicated enough for an adder.
It doesn't have 4 outputs either.
That is true. And then a subtractor is an adder, but one of the inputs is not, and then you add one.
Yeah, and it also, same thing, it doesn't have 4 outputs. That'd be just too many. So it's either a 2-bit compare or it's a decoder. So, why is it a decoder?
Compare would only have.
A compare would only have 1 output, you're absolutely right. It would just have a, is it compared or is it not?
Yeah.
And then the Z in this case, for the decoder, what it does is it decodes what these are. So like, this one is 0, 0. This one is active when it's 0, 0. This one is active when it's 1, 0. Yeah. Where this is Y, and this is X. Right? Because that's Cartesian. That's fun. And then this one is 0, 1. No, I should do it the other way around. Whatever. And then this one is 1, 1. So it's a decoder. That's what a decoder does. If you remember, it takes 2 inputs and then takes what they and takes each of their possible outcomes and assigns a value to them. Or yeah.
It activates that particular output,
Yeah. So that's what that is. Nobody has any questions about that because we already know. We eliminated 2 choices, and then we eliminated the compare by I did the truth table, or you could just look at it and go, that's not a compare, because it has way too many outputs to be a compare, because compares only have 1 output, a yes or a no, a yes or no, it doesn't, which one's greater kind of thing. So problem 55. We'll go back to the beginning over here. I should bring the book with me. This is a nicer section than last time, huh?
Yeah, just a little bit.
Just a little bit.
It's just like the whole test, digital logic.
Yeah, let's do that. Let's talk to Dr. Shu, see if he can just give us a digital logic test.
Yeah.
Digital logic final for our FE exam. What did I say we're doing, 55?
Yeah.
It is.
Yeah, okay, so determine the logical values of the output of the following circuit.
1 or 0.
X is just, oh, I'm dumb. This is not where X goes. This is a full adder. Whoa, I can't write. Oh, I'm gonna do Dylan's idea.
Perfect.
Alright, and then this, the same thing. Oh, I can't. Oh my gosh. I'm going crazy.
Pointer.
What?
It's a pointer and a pointer.
Yes, it's a pointer. We're, that's not bad, is it?
Depends.
I think that's right. Nope, that's not right. Okay. This is X, this is Y, this is Z. We want to know what it is, how it works. The arrows are kind of in the wrong direction. This is the lowest bit, this is the highest. So you add this way.
Okay, the carry.
Yeah, they're carrying, so the carry comes over this way, which actually isn't shown in the, well, I guess it kind of is, there are lines going across. But anyway, so there are carries that are involved. So this one is a 1. This one, you add 2 ones to get a 2, which is actually 1, 0, right? So we take the 1, we put it up this way, and we get rid of it. And we're left with 0. Then we come up here, we add the 1 up here. And so we have 1 plus 0 is just 1, so this comes down 1. So we come out with 101, which is what? A binary name, yeah, that's fine. Woo. So that's not what our question was asking. Our question was just asking for this. There we go. Now we're on problem 56. You know, Jeremy should have been here by now. Okay.
Was he
Problem
gonna,
56. Hmm?
was he gonna teach some of them, or?
No.
Oh,
He actually didn't even help me with most of these. I did them by myself. All by myself.
good for you.
Anyway, determine the value of j after the execution of the following program segment. So we have j equals 1, and if that was the end, that'd be really easy. And then we have 4, I equals, I'm gonna write it exactly like it is so you guys can see how bad this is. 1, 2, actually I think it's capital.
J times I.
Yep. So we're looking for the, actually since it's a computer they did asterisk, which means it's like this.
J star I, what?
Yeah, it's dot product, right? Because they're vectors. All right, so at the end of this program, what is j? So we start out with j equals 1.
6 factorial.
6 factorial. 1. Then we have times 2, times 3, times 4, times 5, times 6, which is 6 factorial. Yeah. But I'm going to do it a little slower for the video in case anybody's confused. And they go, but I don't understand how you got 6 factorial. That doesn't make any sense. So we start out with 1 times 1. Then we go 1, which is 1, right? Then we're on I equals 2, so we're 1 times 2, which is 2. So then we're on 2 times 3, which equals 6. Then we're on 6 times 4, which equals 24. Then we're on 24 times 5, which equals some big number. We'll call it star.
120.
120?
Yeah, 120.
Well, I'm not worried about it. No, it's not. No, yeah, it is. You're right. It's 120. Okay, so then we have 120 times 6 equals some other number. 720.
Yeah, 720.
Solved. Proven. All right. What problem are we on?
I don't know. You didn't write the problem number. Yeah, it was 55
55,
and 56.
56. Okay, so now we're on 57, which is a Q, or I don't know, how do you pronounce this?
Q.
Q. All right, so a queue is a data structure that processes elements in the following order. Is it first in, first out, last in, first out, middle in, last out, first in, last out? I'm going to write it down since maybe you didn't catch that the first time I said it. We have first in, first out, last in, last out, and those look totally different. It's not just one letter, it's in between, it makes it different.
I think they're both right. But we don't
Maybe
say
that's
that.
not.
We don't say last and last out.
Hold on. Did I not say that? No, I didn't say that. You're right. Yes. Last in, first out.
I like the middle one.
Then we have middle in.
What does that even mean?
Last out. Then we have, where am I? First in, last out. Which is the same as this one, so we know they're both wrong. And then it's obviously middle in. It's obviously middle in. So we're left with this. If you've forgotten, both of these are stacks. So if he tricks you up and puts a stack on there, you know what a stack is. Very simple. Like I said, this is the part of the test that you're going to get right. I hope. I really hope. Because if you get problems like this wrong, there's no hope. Right? Right. Problem 58. For virtual memory systems, large programs are executed in memory. They can be executed using a smaller memory space. And they're paged in. This is paged in and out of memory, I think is the of unused video memory, I think is what it's called. Why they call it video memory, I don't know why. And run faster due to fewer disk excesses. Whoa. There we go. One of those is true, the other three are not. For virtual memory systems, large programs, one of those. If they don't run faster due to fewer disk access.
I mean, you're not reading discs though.
You are, you're not reading disks because you're doing this one, the third one. Because, no, sorry, that's not right. It's because you're doing the second one, because you're paging it in and out. I don't, this problem,
I didn't understand the question.
it's kind of weird, yeah. When I first guessed, I guessed this one because they're paged in and out, you know, you page part of it in, page part of it out, kind of thing. So that you use smaller memory that way, but I don't know. Anyway, that's the problem. The answer is this one, for some odd reason. Which of the
Memorize it.
following is not a programmable register? So I'll put programmable register. Oh, it gets better. Don't worry. That's not the question. Zero register is not a choice. But you'll like these ones. The first one is an ALU. The second one is the PC. The third one is the IR. And the fourth one is the MAR. The heck are those? What's an ALU, fellas?
That's a logic unit.
It's a logic unit.
Arithmetic.
It's arithmetic logic unit, in fact.
It's not even a register.
It's not, and that's actually the answer. Wow, that was terrible. I can do better. Okay. But this one is the
PC points to the program.
program count.
Instruction,
Yep, program count, which is a register you can access. Finally, we're on problem 59.
Just in
We're literally on problem 59. Alright. Hold on.
I'm taking over really quick. I just step
57, 58. I've kind of forgotten to keep adding numbers to my problems while I go on. And this is, where am I?
Yeah.
Okay. This one is, I think it's internal register. That's so generic. It's an instruction register,
Okay.
which is still generic.
Is that what maybe reads out of the PC? Like the PC will load the instruction into a register?
Yeah, the PC will load the instruction into the register, I think. That makes sense.
I feel like you don't need
I,
to. Maybe
I'm not gonna
maybe it
question
could
it.
be useful. I don't know.
I kind of like the internal register, but
It's the most awesome register, right?
and then this one is the this one is the most awesome register, also known as the memory
Access.
address.
Aw.
If it was the memory access, what would this one be for? Okay, so those are the four. Obviously, the ALU is not something you can program. You also can't program, or you also can't program your personal. Well, you can program your personal computer. So, even if you got that first one wrong.
You can't program political correctness though.
No, you can't. That's correct. It's correct. Unfortunately, much to the yes, of politicians. Okay, so now we are on the last problem, and we are 15 minutes ahead of schedule, so that's good. Does not reflect the views of the people or the corporations involved. Does not represent CBU as a whole, but represents just the views of certain select individuals. How many ASCII characters can be transmitted in 5 seconds? So ASCII chars in 5 seconds on a 64 kilobyte communications channel. Yeah. Assume 1 bit per character is used for parity checking. So, yeah. Does anybody know how big off the top of their heads ASCII characters are? Jeremy, do you know that? No. Where'd Dylan go? No. He left. He bounced. No, he didn't bounce. His stuff's still here. I don't know. Okay, anyway,
4?
Is it?
I had to look it up. It's actually 7.
7.
It's 8 because
Say,
they include
isn't
the
it hex?
parity.
Okay.
Because they include the parity bit, but for our purposes, we're adding the parity bit later, so it's only 7.
Huh.
So it's 7 bits to represent an ASCII character. Because if you think about it, there's what,
Is
256 different ones?
And so usually it's in hex, so
No,
or they
there's 128.
provide it in hex.
128 different ones, so that'd be 7. Anyway, so there's 7 plus 1 equals 8. And so we want to know in 5 seconds how many of these 8-bit things we can send. So we're assuming in 1 second we can send 64 kilobytes of stuff, I think. Yeah. 64 kilobytes. So that's 64,000 divided by 8 bits per char. It's actually what?
It's 65, 5, 36.
Oh, well,
2 to the 16.
wait, seriously? Hold on, then you're gonna have to do this math because they just used 64,000.
Okay.
They cheated, that's fine. Times 5 seconds, right? Which comes out with 40,000, and your number might be slightly different.
40,960.
Is what you got?
You use.
Wait, seriously? You got 40,960.
Yes. Is that one of the answered options?
Yeah, it is. It's not the right one. Huh.
Don't use 2 to the 16.
Don't use 2 to the 16 when it says 64 kilobyte. or kilobit, actually. But, so do not, this should be small b, because that's important, actually. So, because if this was kilobyte, then this needs to be 2 instead of 8. Because a byte equals 4 bits. Is it? Oh, it is 8, you're right. So, you're right. Okay. Last time I say something. Almost last time I say something. I have one other thing I want to say. If this was an integer character, do you guys remember how many bits are in an int? I had to look it up, so don't feel bad if you don't remember. But
Oh, it's, 2 million, 32? No. I mean,
it's not 32. Long is 32. The 16, yeah. 16 bits are in an int. So if this problem was exactly the same except it was an int instead of a char, it'd be half as many. Yeah. That's all I got. That is the end of the problem. End of the problem set. I did want to ask you guys. We can turn off the video too.